Great. Well, it's wonderful to be here, and I'm very grateful for all the kind words that have been said. Let me just clear my screen a bit. Okay, so what I'd like to talk about today is what I'm doing now, and it is related absolutely to the fourth paradigm, e-science and open science. So I'm very surprised and amazed that people have taken up so enthusiastically the ideas of John Taylor for e-science, the fourth paradigm, and open access. Open access is not what I'm going to talk about today, but it is something that I care about quite a lot. And one of my acts as head of department of my department of electronics and computer science was to appoint a certain Stephen Harned, who was one of the prophets of open access. So I was very much heartened by Professor Raghavan's talk on open access, and I think it's a very important thing, but I'm going to leave that topic and move towards the data topics, and I think that's a key area for libraries. And I should explain that although I'm not a librarian, I'm married to a librarian, and she's also been involved in the University of Washington in Seattle with their iSchool. So I have been kept in touch, and I feel libraries are particularly important for the universities and research institutes, and I'd like to make sure that they retain a central role in the process of research, and that's what I'm going to talk about a bit. But first of all, let me talk about what's happened very recently. So AI for science. AI, I mean machine learning, all the other technologies. So it's a catch-all. It isn't just artificial intelligence, it's machine learning, which is a subset of artificial intelligence. It's deep learning, which is a subset of machine learning, and so on. So all of these things come together. I call it AI for science. So what's happened in the last 5 or 6 years? Well, what's happened is a true revolution in artificial intelligence and machine learning. It's called the deep learning revolution, and it started. We've been doing machine learning for many years, and we have many methods, and I've listed some of them on this slide. And one of them I've highlighted in red because of the work of Professor Fei Li at Stanford University with her Imagenet project. And this project was to get a large number of images, you can see them here, and have them labeled by people using Mechanical Turk, labeling this is a dog, this is a cat, this is a bird, and what type of bird it is, and so on. So they had detailed labels on all of these images. And what was discovered was that we have well-known neural networks have been around for many years. Typically, they have an input layer and an output layer, and 1 or 2 intermediate layers called hidden layers. And what was discovered by using this huge array of labeled images was that you could really make progress because of the scale of the data and the scale of the computing, and you could actually train multiple layers in the middle. And so that really was a true breakthrough, and it's illustrated by this slide, where you see on the left some of the pictures in the Imagenet categories. So you have 1,000 categories and 1 million images, and they're quite detailed. For example, different types of bird, different types of cat, and they're labeled. And when they started the competition, which was a challenge to the computer vision community in computer science, what happened was that the computer vision systems did not do very well at identifying these. But as you see, they got slightly better until a dramatic thing happened in 2012, when there was a sudden dramatic drop of about 10% improvement in the system. And that was because they started doing multiple hidden layers using neural networks to do the job of recognizing. And as you see on the image on the right, that's got much better, and human error rates are around 5%. And the latest networks, before the competition was closed and stopped because they'd solved it, they can now get around human level recognition rates with their neural network systems, which have a huge number of layers. So they have not just 1 or 2 layers, they have now over 100 layers in some of the systems, and they can get down to really impressive levels of recognition. So they've really done, I would say, better or equal to humans in classifying these images. And that was really a breakthrough, and one of the major things. This is a slide illustrating why deep learning is rather important, and why it's important with the data. As the data really gets large, you see the strength of the neural network. Older learning algorithms, as you increase the data, they actually saturate. But deep learning, as you increase the data and the computation, it gets better as you go on. And so this is obviously some sort of marketing slide, because there are no units on the axes, but you see that deep learning is distinguished from the other algorithms for doing certain types of things. And if I look at the sort of things that they've accomplished, this is what the industry, this is Microsoft, this is Google, Facebook, all these major IT companies, they've now achieved near human level image classification, speech recognition, handwriting, they've done machine translation, text to speech conversion, and all these sort of things. And these image recognition will enable, near human level driving. So you'll have driverless vehicles of various types. You can also now have solved one of Google's subsidiaries called DeepMind can now play Go better than the best Go players in the world. So that's a remarkable achievement using deep learning. And also for image analysis for things like cancer in health informatics, they now get as good a result as if you have an expert looking at the image. So remarkable achievements, all these achievements based on deep learning. And that's why everybody's so excited about AI, because deep learning has made really, truly interesting breakthroughs. But all of these, of course, are what the IT companies are interested. What I'm interested is in AI for science. So let me talk a little bit then about the fourth paradigm in e-science. And I think they're both about large amounts of data from science and data-intensive scientific discovery. And the book was published in 2009, and it's surprised myself in its wide dissemination and impact. So I'm grateful for the recognition in India, and I'm sure I will learn a lot from this conference. So I'll give you my personal views of these things. So we're all familiar, this is an old slide, because I was doing e-science in the early part, 2001 to 2005. And at this stage, this was big data. But actually, of course, we've got much bigger now. But nonetheless, there was a tidal wave of scientific data on its way, and that was clearly going to be an important driver. And my colleague Jim Gray in Microsoft used to say that some scientists he went to work with, they were drowning in data. How do they manage how do they manage a petabyte? How do they analyze it, and so on? And so he really believed that there was a new way of doing science. We know about experimental science since the Egyptians and so on, looking and describing natural phenomena. And then with Newton and Maxwell and Kepler, of course, theoretical science came about. So you could do science by doing predictions and testing them experimentally, and from experiment you get new facts, and then you can actually try and fit them into new theories. So that was the way we'd always done science. But in the 1950s, we invented digital computers, and we were able to simulate things that we couldn't do experiments, like galaxy formation, like climate change, and so on. So these are things that you can't do any other way but play with a computer simulation. And that required people with different skills, knowing how to program, knowing how to do algorithms, knowing how to do numerical methods. But today, one of the major challenges is that the scientists now have data sets which are huge and difficult to manage and difficult to extract. What are the important areas? What are the interesting results that you've got in your data set? And they come from all sorts of things, instruments, large and small. So things like the Large Hadron Collider in CERN in Geneva produces petabytes of data per year. And similarly, the big synchrotrons that I'll talk about, they produce petabytes a year too. And there are now, petabyte is now becoming a fairly common amount of data that you receive with these big experimental systems. And for me, e-science, John Taylor gave the, as Professor Urs has discussed, John Taylor gave a definition, and he gave that, gave the program for me to run. And so I had to develop John's ideas into what we meant. And it's what I would now categorize it. It's putting the set of tools and technologies to support collaboration and managing data and things. So it's very similar to what Shalini talked about in her talk. It's a bedrock of the way we're going to do science in the future. So I think they're all important, and data-intensive science is, I think, a genuine new discipline which actually requires new skills, managing data sets and understanding data mining, understanding data visualization, and so on. So that's how I now describe e-science and the fourth paradigm. But I'm quite happy that other people take a different view, because I think that's healthy, and I will learn from the way other people have taken these ideas and developed them further. So this is where I work now, and the reason I work here is because the systems, for example, the diamond light source is a synchrotron which produces X-rays, and that produces petabytes of data, terabytes typically, but now with the upgrades, it's going to produce upgrades not only in the machine, but also in the detector technology, where the data rates, collection rates are increasing faster than Moore's law. We're having huge challenges in dealing with the data sets we create there. And similarly with the electron microscopy facility, there was a Nobel Prize for cryo-EM microscopy, and that also generates petabytes of data. We have also a neutron source. Typically they have smaller data sets, terabytes and so on, and a central laser facility. And we also have, in the building where I work, we have the LHC particle physics data shipped from CERN, transferring petabytes of particle physics data from the LHC in Geneva to us to distribute to the universities. And we also have an environmental data center which archives much of the data that's used for example, for climate change predictions and satellite imagery and so on. So they have petabytes of data on what's called Jasmine. So what we've set up in response to the challenges we have is a scientific machine learning group. We call it SciML at the lab. And our vision is to try and apply methods to the data being produced in all sorts of fields of science, materials science, environmental sciences, particle physics and astronomy, of course, but also the life sciences. And so these are it's a very broad possible areas of activity. And I'll just give you a few slides showing the sort of things we've been doing. I won't go through them in detail, but I'll make sure you can certainly have a copy of these slides after the talk. So our focus areas for scientific machine learning are three. One is the use AI to understand experimental results. And that's sort of, you have the data and then you want to analyze the data, and the modern methods and deep learning and so on can help you get science and recognize patterns and recognize new effects in the data. The other one is the actual facilities themselves. You can actually use machine learning to make the facilities more efficient, to make them actually more automated, to make them generate data better and quicker and generally look at failure rates and understand how you can avoid failure. And lastly, we believe that using AI in scientific examples like these, we can actually advance artificial intelligence methods themselves. So in the science landscape, we've looked at cryo-electron microscopy, neutron data, analysis of satellites and clouds. It's called cloud masking. The way that cells migrate and circuit and create them. It's cell migration when you generate new cells, and then you can also in improving the experimental data, you can use denoising techniques to make the data better. So you can get better results by using modern machine learning and deep learning techniques. We can also improve the way facilities operate. Just to give some example, you can actually control, as you do X-ray of your sample, you can understand what's happening and you can move the sample. You can do on the fly data-driven control. Similarly with neutrons, you want to know whether it's a gamma ray or a neutron. You can actually determine on the shape of the pulse, and that's what machine learning enables you to do. And we're looking also with the laser facilities. When you have big lasers, you can actually, they destroy some of the optics. If you can assess the damages more early, you can stop and change parts before they become very seriously damaged. So all of these things are useful things for experimentalists. And the last area where we hope to learn more about AI, if we can find out how these AI and machine learning methods work on different types of problems, and where they work well and where they don't work so well, we can understand how we can improve them. For example, if you're doing machine learning for science, incorporating scientific knowledge into the computer science algorithm. Can you have a neural network which incorporates the constraints of biology and chemistry and mathematics? Those are the challenges that we have. And what we're looking at that, therefore, is producing a whole set of, I would call them curated data sets. So curated data sets from all of these areas, and we're going to use them. The release is going to be next week, our first official release. We've had a preliminary one, and the idea is to release this so you can go and use this data, and you can actually go and see how your algorithm does with different systems and how you might improve it. So this is the challenge that we hope to learn more about, what AI does well and where it needs improvement. Okay, so that's what I'm doing now. And again, it's all about data. It's all about scientists with large amounts of data. What I want to talk about is pick up some of the other topics of the conference, talk about open science. So I'm not going to talk about open access, other than to say what I think is one of the seminal events in the last decade, which was in 2013, where the US White House issued a directive to the US funding agencies like National Science Foundation, Department of Energy, to develop a plan to support increased public access to the results of research funded by the federal government. And this was significant in that the results are not just the published paper. The actual memo defined digital data. And this was the recorded factual information necessary to validate research findings, data sets to support the publications, and so on. So it was really pointed out to the fact that public access to the results means not only the research paper itself, but also the data supported. So this was actually, the agencies had to think about how they were going to not only get open access, but also how they were going to link that to the data, and you can get the data sets on which the paper was based. So that, I think, was a very important, it's taken time to get moving, but I think it's going to be a major challenge. And I was very interested in Professor Raghavan's analysis for open access in India, something I've cared about for some time, and it's an important area, how we get open access. But I'm not going to talk about that. I'm going to talk about the data. And in principle, in 2016, a group which Microsoft was one of the funders of their original meeting, was at the FAIR principles. And this is so generic. You want your data to be findable, you want it to be accessible, you want it to be interoperable so that you can actually use it and bring data sets together. And lastly, if you've made all this data and curated it and put it in a database or an archive, a digital library, you want it to be reusable. So these are the challenges. FAIR principles sounds really good, but we need to figure out exactly what we mean by that. And I'd like to just say a few things about this. I'm not going to talk about it in detail. There's more information on the slides than I'm going to go through in detail. So let me just quickly run through some of the things that I think are important. So this is data discoverable and usable at scale, findable, accessible, interoperable, and reusable. And this is where it was published, scientific data. Susanna Sansoni is one of the editors on the editorial board of Scientific Data. Set of principles to enhance the value of all digital resources and its reuse by humans and machines. They're very insistent that you can make these machine readable, so the machines can find the data and then understand it well enough to interoperate with other data sets. And that's a key thing. So I'm really going to focus on the I of FAIR. Findability, I'm not going to go through this slide in detail. Metadata catalogs are clearly important, and EOSC is the European Open Science Cloud project, and there are two other projects that are relevant for the data I'm discussing. One is EXPANS, where PAN stands for photon and neutron data, and the PANOS, which is the Photon and Neutron Open Science Cloud. So these are some of the projects looking at things like findability, metadata catalogs. Accessibility, you need to have authentication, authorization, a DOI for data sets and so on. And that's, again, an important area where you can spend a lot of time. What I'm going to do more is focus on this one, which is rather, in my view, less defined, because as you can see on this list on the left, data meaning and context requires semantics, and you need vocabularies or ontologies, and how do you use these to make the data machine interpretable? And that's what people are caring about here, and I'll say more about that later. And lastly, reusability. So you need the provenance, you need descriptions, you need standards, all of those things, and facilities and institutional policies are obviously important. So those things are important, but I'm not going to go through them in detail. So you've got your data set, you've got some metadata. Is it fair? And so now there are people actually trying to evaluate how fair your data is. I'll just pick out one of these things. This is reusable fair implementation profiles, and they want to see if they can publish what they call FIPs, fair implementation profiles, to accelerate convergence. But just picking out one sentence from this paper, principle I1, that's interoperability, requests that a formal, accessible, shared, and broadly applicable language for knowledge representation be used to embed machine actionable semantics. All right. And so they suggest technologies such as the semantic web technologies of RDF and OWL, but also the other languages possible, Rule ML and Psych, but it doesn't actually tell you have to use a particular one, but it does talk about the machine actionable semantics. And at the moment, I think these are beyond the interest of most scientists. Biologists have made a great start in some of these things with RDF and OWL and Sparkle, but most people don't use those. So I think there's a challenge here, what I actually means. Just to give an example, this is on the right, Professor Simon Coles at Southampton. He runs a national service of crystallography of small molecules. And so they produce large amounts of data, and he works with large numbers of researchers across the UK and elsewhere. And these are his comments that I got in 2015. Much of the take-up of ontology, RDF, Sparkle, and OWL in chemistry has been very slow, but in biosciences, it's done very well. But what he would like to state is that they have well-established format called CIF. It's a format which allows you to do not only high-level discovery, but also you can process it as a rather low level. So he would say that they've really been doing FAIR for 20 years. So he thinks crystallography is a shining example of FAIR. What hasn't happened, he would say, is the reuse by other parts of chemistry and physics. But this is his view of what the I in FAIR is all about. You can do it with using this chemical format CIF. This is, when I was at Microsoft, this was the only standards area that Microsoft and Google agreed in. It's schema.org. And the idea of schema.org is to give a little bit of semantic information. So for example, if you're looking for Casablanca, there are 2 sites which mention Casablanca on the web. One of them is about the place in North Africa, and the other one is about Humphrey Bogart's movies. And the question is, you'd like to be able to distinguish. And this is a thing which allows you to mark up your websites with a small amount of semantic data. So you know this is about a place and this site is about movies. And you can actually therefore understand what, to some extent, the websites are about. So it gives you a little bit of semantic information. And that's been built on by the biology community. Carol Goebel and Rafael Jimenez in the Elixir project. They've actually decided to, what schema.org allows you to do is to add your own terms to it. So they've added in their bioschemas a vocabulary that's useful for them in biology. And so bioschemas for genetic types and biological types, these can be added. And furthermore, instead of having to use exotic technologies from computer science like Sparkle or OWL and so on, you can actually use a much more familiar technology with JSON, and JSON linked data actually enables you to put these things into practice much easier, such that you can actually now, with bioschemas, they've worked with Google's dataset search tool to make sure that using their bioschemas, their data can be picked up by Google's dataset search. So they've worked with the dataset search people and schema.org extended with the biology bioschemas to make sure you can actually find all their data sets. And that seems to me, yes, you don't get all the semantic information, but you do get some semantic information. And of course, it's never going to be perfect, but you get a fair amount. So I think this is a very practical way forward. And this is what Rafael Jimenez said in 2015. Just to read a bit of it, he's a supporter of RDF, but it's been difficult, idealistic, and for a small community of semantic geeks, JSON LD has easier, practical, and wider technical audience. So we should hope for all our data to describe and expose all their metadata. It's important to set priorities and provide guidelines to start exposing at least the minimum metadata that will help machines and people find data. So it's a step on the road, and it's stepping back from doing everything using semantic web technologies. Okay, so those are some of my concerns about the I, that there are really some really big semantic issues you have to worry about. What about the progress towards fair data? Are we making progress? Well, European projects, there are a large number of European projects. I've talked about EOSC, the European Open Science Cloud. I talk about PANOSC, which is the Photon and Neutron Open Science Cloud. And there are other projects that are important in this space. What we're doing at the Rutherford Lab is working with the Diamond Synchrotron and Susanna Sansone in Oxford and Steve Collins, who runs one of the beamlines at the synchrotron, to see if they can actually make the human and machine agents gain access to data coming from the synchrotron in a way that's complete, has the provenance and has semantics. So the idea is to see if we can really do that. And in 2022, Diamond has a policy that they're going to make all their experimental data publicly available. So we'd like to understand what you need to do to curate it, to make it fair, and so on. So this is an experiment and exploration, and it's just starting. And if you invite me back in a few years' time, or invite Steve Collins or Susanna, they can tell you how it went. One of the NSF projects on data was called Data One. It was the only major data project that continued for the full 5 years. And it was originally about ecology, enabling new science and knowledge creation through universal access to data about life on Earth and the environment that sustains it. So it has now a way of bringing data sets together. You can search across multiple data sets run by other people. You don't actually have to have created it in one place, but it's a distributed service. You have data sets in different archives and you can put them together as appropriate. And so what they've done is they have, this is a summary from their website, about 800,000 data sets. Obviously not very large because they're only 80 terabytes, and now we have petabytes of data, but nonetheless, these collection of small data sets, they have a tool which is called a Data One Fair assessment tool. And so they have tried to measure with these data sets how fair they are, and they have a metric, and this is their average score they've got. Findability 75%, accessible 39%, interoperable 63%, reusable 49%. Now, I suspect that purists would not be happy with interoperability in the way that they've defined it for their tool. But this is a point we're going to have to grapple with, because fair sounds so good. All the agencies are saying your data needs to be fair. We need to define what fair means. This is what the astronomers have done. They certainly haven't used FAIR very much, but they have got the International Virtual Observatory Alliance, which has set up standards. And these standards have really revolutionized the way astronomers deal with their data and how they can share it and make them interoperable. So data from different telescopes can be actually combined and used. And so this is a key area for astronomers rather than FAIR. FAIR is recognized, but they haven't really done very much on these sort of semantic issues. So the conclusion I have is that, and this is from Susanna Sansoni, who was one of the original authors of the FAIR principles, that the FAIR principles are, at the moment, they're aspirational. It's not a standard, but it's a set of guiding principles that provide for a continuum of increasing usability via many different implementations. And that means that I think the library community and the community we have in India is actually can play a major role in understanding what works, what doesn't work, where we need improvement, and working with your data sets that you've got curated in your archives and digital libraries. I think it's an important and interesting area. So that's all I want to say about FAIR, but I thought I should say something about my feelings about the role of research libraries. Because I'm married to a librarian perhaps, but I do care very much about libraries, and I've been concerned that libraries used to be the focus of a university. It was the heart of a university. You couldn't conceive of a university without a physical library. Well, nowadays, you can conceive of a university without a physical library. You can do things online. Your journals go all online. You could, for example, in the UK, you do not need to have huge numbers of volumes of 1930s, 40s and 50s issues of physical review or chemical review, because there are digital versions in the British Library, for example. And so you can access those rather than having to have the physical volume locally. You can have the physical volume in a few places and you use electronic volumes. So libraries have to change. And so in my team at Microsoft, I had a couple of librarians and one of them I'll tell you about in a moment. But this, I went yesterday to our university library. I live in Southampton, and this is what you see. On the wall, you see in the library, there's Latte's Cafe Bar. And you get lots of people coming in to use Wi-Fi, to do coffee and things like this. And that's fine, it gets people in the library, but that's not what a library is for. And on the right, you see a recent addition to the library, and it has these racks and racks and racks of ancient volumes of books and journals, which are, I would say, are never consulted, but that's probably a slight exaggeration. Maybe some of these, this is only a small fraction of the ones in this particular extension. And it really is not the vision of a library of the future. This is a library of the past. So this is where I see things. You have now lots of services you can get from the cloud. You have lots of services you can do online, visualization, blogs, instant messaging, compute services, knowledge management, document stores, scholarly communications, all of these things electronically. Where on a university is the library? What is the role for research libraries? And that's the thing that has concerned me for some years. I have to say, I have not succeeded in doing that at my own laboratory, the Rutherford Appleton Laboratory. We are not in the forefront of this. We should be, but we're not. So I'm still working on this, but this is what I think is one of the roles for the research library. This was a slide for the librarian Lee Dirks, who worked for me. Unfortunately, he died in a car crash, but he introduced me to many things, and this is a slide he liked using. Commercial entities like Google and Microsoft and others are now in the library space, whether you like it or not, because they can find articles and you don't need to go to the librarian to find an article on archive or whatever. I was Dean of Engineering at Southampton, and my students rarely went to the library for library purposes. They went there for Wi-Fi, for coffee, a meeting place. Surprisingly, Margaret Hodge, Britain's former culture minister, this is what she said: sleepwalking into the era of the iPhone, the ebook and Xbox without a strategy, she suggested, runs the risk of turning the library service into a curiosity of history, such as telex machines or typewriters. And General Shinseki was a general, obviously, in the US Army, but he was also in charge of the Veterans Affairs in the States, where they have huge amounts of data. It's the biggest thing to a national health service in the US, the Veterans Affairs. If you don't like change, you're going to like irrelevance even less. So have librarians abdicated? I don't think they have, but I think the ones certainly that I've worked for in the UK have been rather slow. This is a slide from the MIT DSpace project. Mackenzie Smith, who's now librarian in University of California at Davis. Much of the material produced by faculty, such as data sets, experimental results, rich media data, as well as conventional document-based material, is housed on an individual's hard drive or departmental web server. Such material is often lost forever as faculties and departments change over time. So I do think there is a role for doing this. An important role for research libraries should be the guardians of the research output of the institution, to keep what could be important, where you could have, for example, intellectual property. So this is an important role. However, this is what I think is one of the key roles. I also asked Jim Frew, who's a colleague, environmental earth scientist at University Santa Barbara, California, Santa Barbara, in 2015. And I asked him whether there'd been progress in environmental data curation in the previous 10 years since the eScience initiative. And this is his response. The biggest change is now funding agencies like the NSF insist on a data management plan. So they have a data management plan. You have to put words in your proposal. And he believes that's made scientists possibly pretend to take data curation seriously. I asked him if there are now better curated databases. He said, yes, there are, but there are many more databases. So he wasn't sure that the fraction is increasing. And he came up with what he called his laws of metadata. Scientists don't write metadata, to a first approximation. And secondly, any scientist can be forced to write bad metadata. And so his conclusion was you should automate the creation of metadata as far as possible. But scientists should work with the metadata specialist, who used to be these subject librarians in the university, and they can together develop a sensible metadata for their particular data set. So I think the libraries have a role in making scientists curate their data better so they can actually find things, you can actually do things with their data, as opposed to just storing it in files with no metadata, which is almost like throwing your data away. So I believe that the libraries of the future, research libraries, need their metadata specialists collaborating with scientists. And if they need more metadata specialists, then they need to retrain and refocus their efforts. So that's my personal view, and I hope that I'll hear a lot more in this conclave. So let's just finish. The transformation of scientific research. So where are we aiming? Why am I doing AI for science? Well, I do believe it has the possibility in the next 10 years to transform much of the way we do research with experimental data. And one of the things that convinces me more about this is Google have a subsidiary in England called DeepMind, and they've been attacking not many scientific problems, but big, important problems. And so the protein folding problem has been around for many years, and they have a competition every 2 years with the people who do protein folding to see if they can predict, if you know the chemical composition of a protein, how will it fold up in three-dimensional space? What will the shape of the molecule be like? And that's what they've been trying to do for 50 years. And AlphaFold, they did originally 3 years ago, but last year, AlphaFold 2 really won 3 years ago, the competition, and last year it did even better and was really spectacularly improved. And you can see how people reacted. This is John Moult on the left here, stuck with this one problem: how do proteins fold up, for nearly 50 years. To see DeepMind produce a solution for this, having worked personally on this problem for so long and after so many stops and starts, is a very special moment. And then the ex-president of the Royal Society, Venki Ramakrishnan, computational work represents a stunning advance on the protein folding problem, a 50-year-old grand challenge in biology. It has occurred decades before many people in the field would have predicted. It will be exciting to see the many ways in which it will fundamentally change biological research. And lastly, from Genentech, a company, AlphaFold is a once-in-a-generation advance, predicting protein structures with incredible speed and precision. This leap forward demonstrates how computational methods are poised to transform research in biology and hold much promise for accelerating the drug discovery process. So this really is a significant event. It involves huge amounts of data and work and so on, and computation, but also deep learning. Deep learning is the AI magic that makes this work, and the computation that you need to go with it. You need large amounts of computation, and that's actually beyond the reach of most universities. So the question is, can we do something which are similar breakthroughs in other areas? And similarly, we also talk about self-driving cars, but actually self-driving laboratories, autonomous control of experimental systems. You can automate the entire experimental workflow, setup and tuning of the experiment, sample selection, measurement, data analysis, and model-driven data interpretation. And then you can also follow up with saying, what experiment should you do next? So there's huge amounts of efficiencies and exciting things you can do by automating various parts of these laboratories. And these self-driving laboratories will, I think, be an important feature of the future. So those are just two examples. The last example comes back to Jim Gray, for whom we actually produced the Fourth Paradigm book. All right. And so his vision was of, you can go from the literature, which obviously he was a big passionate advocate of open access and worked with the National Library of Medicine in the US, which actually was one of the pioneers, and Jim Gray worked with them. And he wanted to go, as they do there, go from the paper in the National Library of Medicine. You can go to the data that produced it. They have lots of databases. You can add your own data and you can put those together, do more research on that and publish a new paper and so on. So go from literature to computation to data back to literature. This was the sort of cycle he thought you could dramatically speed up. And information at your fingertips for everyone, everywhere, huge increase in scientific, what he called information velocity and productivity. So these are the things that I think are within reach. And one of the challenges, of course, you can do more with just the literature. We've talked about semantics on the data, but you can also do semantics on the papers. Can you have AI systems that can actually understand the science in the papers rather than just pick out keywords? So those are many challenges, but I really believe that we're poised in the next 10 years to make dramatic efforts. And my last slide is a serious slide, but will not be welcomed by all scientists. AI will not replace the scientists, but scientists who use AI will replace those who don't. This is adapted from a Microsoft report, but nonetheless, I think this is something that librarians and information scientists also need to think about, because I think you can call those as the generalized scientists. Thank you very much for listening. I better stop.
There are 3 questions posted here. Before that, there is a, let us take the one who has raised the hand. Dr. Shalini has raised her hand. Madam, could you please ask your question?
Hello, Tony. I have a couple of questions, but I'll stick to one question first. In the early part of your presentation, you gave the example of this Imagenet and deep learning, etc. Stanford. One of the things that generally, there was a controversy also is about the biases in all this, systems of whether it is image or even the other one. And there was this controversy of about, how colored people were actually categorized in a different way. So what is your take on that?
My take on that, I gave you the headlines, but I didn't give you many of the things that concern me. One of which, of course, is when you have facial recognition, they do quite well on white people, but they don't do well on different Chinese or Indian or other colored people. So, and that's clearly dangerous, and we are a long way from solving all those problems. But there were also other problems. I mean, you can train a thing to recognize dogs, and then you can sprinkle a bit of noise on that image, so it looks to you and me as nobody's changed it, but now you use the system you've trained to recognize by showing it 1,000 pictures of a dog, and it thinks it's now a toaster. All right, so you can it's a rather fragile system. So I think we need to understand the limitations of these systems, and they're not perfect, and there's a lot of more work to be done. So do they really understand things? What are they picking up? How are they making decisions? So explainable AI is important, as well as the biases that these systems have introduced. And I think those are very real problems.
Thank you.
Yeah, hand is raised by Dr. Sai Baba. Sir, could you please unmute yourself? Yeah.
So I'm audible now?
Yes, sir.
Yeah. Thank you, Professor Tony. Hey, I think your talk made me to really think and go into the future. Thank you for the perspective. But I just started thinking, because you made me to think in the future. Today, we are looking in terms of AI to solve some of the problems which man or humans are trying to solve or take time to solve. And it's exciting. But I was just thinking whether it also would put some limitation when you achieve this. Today, humans would take years and the AI would help you to do it faster. But then what next? What next? And do we foresee certain issues because they're doing it so fast?
Well, I do see certain issues in many areas of AI. One of which that worries me is the fact that AI can reduce the employment. You can automate many jobs, and I think that's a real concern in all countries of the world, because I do believe we need to actually focus on creating meaningful jobs for young people, and that's absolutely vital. So that's a more generic thing. What about science? Well, I talked to someone who was promoting the automatic lab experiments, and he was saying, well, it could be that it's so fast that you run out of ideas of things to do. So I think that we'll see how things go, but I believe there's plenty of understanding of AI methods, what it does well, what it doesn't do well. I think it'll take us quite a time, but I do believe that we will come across all sorts of issues that we haven't thought through. Yeah.
Thank you.
Next one is Dr. Mudkavi. Sir.
Am I audible?
Yes, sir.
Yeah. Professor Tony, hey, actually I got cut off when I was introducing my institute. It was actually inspired by your book. I just wanted to repeat that here.
Very impressed to know that. Yes, I was.
Yeah.
Thank you.
So the book actually gave the title, and the title gave the name for our institute. Like, right. So thank you very much for that. My question is actually regarding the end of theory. So now I just want to draw a parallel, because when the computational systems arrived, traditional mathematical analysis, I think, kind of took a backstage, because people would directly go to computational systems. Of course, algorithm development required some of the computation and some of the mathematical understanding. But in a similar way, if I'm looking at only data-based approaches, will theory kind of take a backstage? Or at least the new theories will not emerge from the traditional way of constructing these theories. Maybe the AI systems themselves will construct new theories, or what is going to happen?
No, that's an interesting question. Yes. So I actually think I've taken a rather narrow view. I'm just looking at machine learning and AI applied to scientific data sets produced by these facilities, and that's one area. But I would actually recommend it isn't all deep learning, just running these machines. There are other new mathematics that you can bring. And if you want examples of that, I recommend a project at Berkeley National Lab in California. It's called the Camera Project, as in camera, and the AM in that stands for applied mathematics. And they've done some machine learning and things like that for their experiments at the lab, like we're doing. But they've also used all sorts of clever new mathematics and combined it. So I do think that applied maths is important. I think statistics is important. Computer science is important. So I don't think it's all solved, or one thing fits all. I think that when we're not seeing the death of theory, and I don't believe that you'll be able just to use Google to find out scientific results. So I think we're a long way from that. Although Google's DeepMind for that particular problem with AlphaFold is an impressive example.
Thank you.
Okay, the question here in that question Q&A box is, I love Frew's law of metadata. As you suggested, librarians can contribute to the creation of metadata. The world seems to believe that AI will take over and librarians are not needed. Once the existing librarians retire, who will create the metadata?
Yes, I like Frew's laws of metadata too. No, scientists need to learn how to create metadata. And I do believe there's a real role for people who understand metadata, like librarians, and especially subject librarians that we used to have when I was at university in Southampton. They can work with the scientists to create metadata. Some of that you can create automatically as you take the data, and that's an important element that will happen. But I think there's always need for a collaboration, and I think that the librarians will, with their repositories, with the curated data sets, they'll be the ones who look after this data. So I don't think existing librarians will retire, but you need to educate and renew that, because I think that you can't do these AI things without serious metadata. So AI is not going to take over without the appropriate metadata on the data sets. We're generating new data sets every day, and I think there's a large role that can be done to go and help the scientists in your university or your institute or your experimental facilities understand how to put metadata such that you can use machine learning and AI methods on it. So I think it's beginning, and there's a healthy cycle where people retire, but new ones need to be educated with the right skills. Just like we need now to create data scientists who understand these things, you need librarians who understand how to work with scientists to create the appropriate metadata. So I think there's a key role there. I really do, and I don't think it's going to go away.
Yeah, thank you. Question need to be asked by Mr. Satyanarayana. Could you please unmute yourself, sir?
Yeah, Professor, hey, it's so exciting to hear your talk. I have one question related to interoperability. And most of the time when we talk about interoperability, we generally focus on metadata, the structured data basically. Now, is there any attempt to look at or interoperability between two different ontologies? Is it possible
Well,
to develop interoperability? Like typically, the Medline uses one set of ontology, chemical abstract uses another set. Both of them index a lot on, let's say, drug discovery. Is it possible to develop interoperability between two ontologies?
I mean, that's a question that's worried me because I was on the advisory board for Data One, and they were putting distributed archives of different types of data with different ontologies. And yet they were advertising they could search across these, but they can't search across unless they've got a common thing. So you want something much more powerful than just the basic commonality. And so that, I think, is an important issue. And I think how these interwork, how we do semantics will be extremely important. But I think one has to recognize that most scientists aren't going to be experts in these exotic technologies, and they need to be brought towards that. And I think that's why I favor something like bioschemas, which is actually rather more pragmatic and takes a small step. I don't know how, I'm not sufficiently educated to know exactly how different ontologies can be matched together and find the commonality. But I think that's an important area, and there must have been some progress in that area. So no, thank you very much for the invitation to this. And I should also emphasize, I've given you my views of fourth paradigm, e-science, and so on, but there isn't the view. There's your views, and your views are just as valid, and you can show that what I should have been emphasizing is this, and I will be learning, I hope, in the future from what you publish.
Thank you.
There's one question from Dr. Debasis Das. Could you please unmute yourself, sir?
Yeah, hi, good evening. Professor Tony, great insightful talk, and I'm particularly attracted to one of your slides, and where you probably mentioned that metadata can be generated automatically. I belong to the field called healthcare science, and lots of people generate a lot of omics research, transcriptomics, genomics, all other kind of life science data. Now, my question to you is that can the metadata be generated other than the people who are directly related to the work? For example, how would one know whether it is a tissue or it is a cell line, or what condition, what kind of treatment has been given? So metadata is very useful, I agree with you, but can it be created by somebody who is not a part of the experiment or data generator?
Interesting question. Yeah. So yeah, I think I can see how metadata can be generated as you're doing the experiment. So you can automate things. So you record things like the temperature, what the chemical compounds are, and those can be recorded as you do the data. So could someone have the data set and then generate metadata without involving the people who took the data? I would be skeptical, but I'm willing to be educated. But I think it's an interesting question. And I do think we need to have a collaboration between the people who took the data and are the scientists with people who generate the metadata. That's my personal belief, but I may be wrong.
Thank you.
There's a question in the Q&A box from Manish Mankad. How much auto indexing is accurate in metadata creation?
I don't really know enough about that to be able to tell you that an answer I would be confident of. So I'm sorry, I can't. I don't know about auto indexing and stuff. I know you can, as you take the experiment, you can record certain aspects of the experimental conditions and so on, and what you're doing, and they can be automated. I don't quite know what you mean here by auto-indexing.
One question is there from Raghavendra R. I was amazed to see self-drive laboratory. Does it going to be reality in coming days through, though we synchronized latest technologies minus of human brain and interventions?
Okay, so I think the self-drive laboratory is a vision, all right? It's not my vision, it's a vision of others. I think that you can do a lot. My personal view is that, this is purely personal, AI, the thing is there going to be something as general AI that can actually make its own deductions and do things? I happen to believe with one of my heroes, which is Professor Licklider, who had the idea of the internet. He was a psychologist, and he believed in a human computer symbiosis. So I think actually I see that AI systems working with humans actually being able to go and do make these decisions. I don't think you can put everything on the AI system, but that again, that's a personal view. Other people think that they'll build AI systems that can do everything. I think that's a long way off. I'm actually being forced to think about the fact, could one imagine an AI system that by the year 2050, well, that's sufficiently far off that I can't think that far ahead, but that was the question I was asked, that could win a Nobel Prize. An AI system, could it win a Nobel Prize by 2050? And I have no idea. I think it's highly unlikely, but who knows?
Sir, one more question in the chat box is there, Q&A box. In the context of e-science, explorations of big data research and scholarly communication, what new roles the librarians are expected to catch up with the shoulder? Must be a subjective question, of course.
No, but it's something I've concerned. What I didn't talk about was open access. So when I was Dean of Engineering, I had to produce an annual report of the faculty research, and I had to search down all the papers that everybody published, and it turned out to be a huge amount of effort. And we didn't have all the journals. By that stage, I got from my librarian, I got a piece of paper saying, what journals would you like to cancel this year? So it was actually true of my staff, 200 staff, 500 students and postdocs. We didn't have the journals that they all published in. We had many of them, but we didn't have them all. So collecting them all together was a pain. And so I asked for the creation of a digital repository for all publications in preprint that you submit to journals. And so that was one of the first repositories for papers. We didn't make it available to the outside world unless it was not a problem with the journal. So this was just to make sure we had a record of everything that our staff did. And that we took up to my old department of computer science with Stephen Harned, and we set up the ePrints server, and we started very early on doing ePrints. And again, that involved the library. My wife was involved with the oceanographers in the library and things like this. So creating repositories is clearly looking after open access, making sure you have a copy of everything your university publishes, or not the grey literature, all sorts of other things. Librarians, that's actually one of their roles that they do extremely well. And for example, the particle physicists publish in arXiv. Now that's, they published before it's been refereed. So arXiv is an unrefereed pre-publication thing, and publication, if you like, is a stamp of approval by the journal. But you then have lots of different versions. But again, librarians are very good. They know how to deal with these things. And to my surprise, this hasn't caused a great deal of problems. So I see certainly the role of digital libraries and repositories. The library, research library has a central role. And I think also with the metadata curation, I think librarians have a central role. So I would like to see research libraries, not for being, irrelevant to the future of the university or the research institute, as being central again to how how the whole institution, library, or the whole institution, the university or the institute should function. And the research library can be at the heart of that process.
Great. I think the next question, I think you must have, whatever answer you have given may be related to the same question. It is there. How allies professionals can understand or develop his or her cross-disciplinary, multidisciplinary, interdisciplinary, interdisciplinary and cross-disciplinary domain knowledge?
That's an interesting challenge. Yes, I think it's difficult. And for example, I've been concerned with scientists who know enough about computer science. Can you have people who know both fields? And it's very difficult. And you have to know enough about one field, and you have to be an expert in one field. Can you be experts in more than one field? That's rather rare. And so I think that requires a great deal of thought. I don't know whether the libraries now you still have subject librarians, and that's what we used to have, and they used to be expert in physics or in chemistry or whatever, and those were the sort of skills that they could work with that community, and they could talk to their colleagues in the library about possible connections. So I think if there aren't subject librarians, maybe there ought to be again subject librarians who specialize and can work with different communities, but maybe they can work with more than one community. But I don't know enough about how the research libraries now are functioning, because I'm at a national lab where we have a library which is very old-fashioned, actually. It really just is concerned with ordering the journals that we afford and getting papers for people, buying books. This is actually not central. We can do all that ourselves. What we need librarians to do is the specialized things that I've talked about.
Mr. Chudamani has raised a hand. Could you please unmute yourself and ask your question, please?
Yeah, I have a question. I'm a practitioner of classification. New research comes. How do AI can handle that in processing, classifying?
Okay, so I know what classification means in the context of machine learning, that you can decide whether it's of that type or this type, whether it's a neutron or a photon and things like that. So you can do classification problems like that. Or are you talking about the traditional library classification schemes, about which I know rather little?
Yes, traditional library classification and AI-based classification.
Well, I'm afraid I'm not educated enough to answer that, and you'll have to educate me in the future about exactly how those are linked together. So I'm sorry, I can't answer that one.
Okay.
Maybe I can just add one comment here. There are, methods are, I'm not saying that they're very good, but methods of, text summarization and classification for documents themselves, which will also help you in this kind of a auto classification. It's not very well developed, but they're there.
Okay,
so it's an extension of the text summarization technology, essentially.
Yeah, no, text summarization I do know a little bit about, because Microsoft had those technologies. So that's interesting. Yes, it is. And a colleague of mine who works at the lab, Jackie Cole from University of Cambridge, she's got a tool which uses natural language processing and can, from scientific papers, get information from the tables they publish and things like that. So she's doing, it's called Chem Data Extractor. So she's doing that type of extraction from papers, but there's also summarization. So there's a collection of things, but I think there's more to be done. And I haven't looked at that part of the whole challenge.
I just want to add a comment here. I think we need to really look into at what stage the classification need is going to be continued. I think with the type of search mechanisms that are becoming available, we need to really address that part of it. Though this may be, it may be a lot of libraries professionals unhappy with my comment, but I think we need to really look whether up to what time we need to continue with this classification. can the search mechanism can help us to find out what we're looking under the classification.
Professor Murkabi has raised his hand, sir.
So if I'm permitted, second question, right? Okay. So I just wanted to ask you one question. That is, we do use, of course, observational data for training the AI systems. But now, for example, can I use, let's say, simulated data? For instance, I'm thinking about, aerospace applications where we want to, let's say, develop a new design for an aircraft. But, I may not have all kinds of, data which is coming from flight test, let's say. So I may actually have some simulated data from a variety of, flight scenarios. Does it add any bias? Because, or you think, it can actually lead to new designs using AI techniques?
No, that's something I'm particularly interested in, because one of the things I didn't talk about was I talked about Imagenet, which they painstakingly labeled them by hand, all these images, by getting people to do it, if you like, crowdsourcing. But when you generate experimental data off a machine, it doesn't come with labels. And so what one tries to do, one example is you do a simulation and you train your system on simulated data. Now, that's fine, but on the other hand, if there's something really unexpected, is your system trained to recognize that this is a real signal which you didn't expect? So I think there are issues with simulated data, but that's what people are using. And there are many interesting things you can do with simulation. You can train a system now to emulate what a real simulation involving, the equations of motion and everything else. So you can actually have these surrogate systems which generate data which looks indistinguishable from the ones that take a lot of time solving the differential equations and everything else. You have these things encoded in a neural network. Now, is that sufficient? What happens if there is some new science there? For example, the particle physicists are looking for supersymmetric particles, and no one really knows what they look like. They think they know, but if it's somewhat different, would they find it? And from all this massive data. So there are many issues like that, which I think are not solved. And so I think there's plenty of work for AI researchers and for scientists to look at these issues. And for designing a plane, clearly that's a rather critical thing to do. But there is such a thing as transfer learning. So you can train a system, for example, on Imagenet, so it recognizes things, and then you can use that trained neural network on another type of problem. And that actually does have some success. So transfer learning, where you've trained it on, for example, on astronomy data from the Sloan Digital Sky Survey, and now you can actually use that as a starting point for training on the data you expect from the Large Synoptic Science Telescope, LSST, the Vera Rubin telescope it's now called. So transfer learning has a possibility of doing things. But no, I think those are real problems that I hope our benchmarks can shed some light on. That's why we're doing things like that, to understand the limitations and the strengths of machine learning and AI.
Thank you.